We are looking at the AP Physics C 2004 E&M free response questions, specifically number 3. This is an induction question, and you will see an induction question every single year you ever take this AP Physics C E&M exam. It will pop up. Normally it's the third question, which is what we're seeing here. What we've got here is a rectangular loop. It has dimensions 3L along these edges and dimensions of 4L across this. Now I'll point out right now, because it'll come back, that it is sitting a distance L away from the wire. So this long straight wire right here is carrying current in this direction, and it's a current I. What we're asked to do in part A is figure out what is the magnetic flux through the rectangular loop in terms of I, L, and fundamental constants. So something we need to remember here is, given by our right-hand rule, looking at this, we know if we put our thumb in the direction of the current of the wire and then curl our hands around, when I do this on my screen, our B field is going to be going like this, okay? On the top of the wire, it is coming out of the page, and on the bottom of the wire, it's going into the page. Now, something we also have to remember, and this is just something that I personally like to remember here, if you want the magnetic field strength, that magnetic field strength is going to change as you move away from the wire. This can be given through us by Biot-Savart's, or Ampere's law, excuse me, which is in a way a Biot-Savart setup. But we should remember that the B field strength is equal to mu naught I, or that current enclosed inside of that loop you're putting around it, over 2 pi r, where r is the radial distance you are away from the wire here. Now, in our case of this, we have flux going through this hoop at different distances. This r value is changing, which makes this slightly annoying. But have no fear. We can think, using for the equation of flux, that a flux is equal to the integral of whatever your field is, and in this case it's a B field, and then that is dotted with the surface area that you're passing through. Okay? Now, this loop that we have is 90 degrees due to the fact that it's a circular loop, so we don't have to worry about a cosine product here, but this is the equation that we need to set up here. We have a value for B. We have this whole setup. But we need to set up a value for dA, which is a little bit weird. We know in general that our area of this shape here could be thought of as just saying 3L times 4L. But in terms of dA, we want to see how a little bit of that area exists as we move along this wire and away from, well, as we move away from that wire. So what's really going to happen if we think about this is we're going to have a stretch length of 4L, and then we're going to put another 4L next to it, and then we're going to take another step and 4L next to it, and 4L next to it, and 4L next to it. Each step we move forward is some distance dr. So some tiny sliver of area we have here is going to be 4L times dr, some small bit of width. And that is our dA amount right there. And that's a huge, important thing that if we don't have that, we're not going to be able to solve this problem. And we need this dA amount because it is in terms of r, which is what we're moving away from, or across this loop, and that's going to cause our B field to change its value. So what we can say here is that this integral now, when we write it, we can say that it's the integral of the B field, which is mu naught I over 2 pi r, dA, which is, why does this keep moving on me? Our dA here is 4L dr. Now there are a bunch of constants in here that we can take out. The mu naught can come out, the I can come out, the 2 pi can come out, the 4L can come out. So this integral can be rewritten as 4 mu naught I L over 2 pi, and then integrated dr over r. Now, one thing that we need to be careful about are what are the bounds of this integral. And this is where this initial extra distance in the beginning comes back. We cannot say that we're just integrating from 0 to 3L because our loop doesn't exist where the wire begins. It exists at a distance L away from the wire, and then it extends 3L further. So this point out here is actually at 4L, and this point here is L, and that is what we're integrating across. So our bounds here are going to be from L to 4L. All these constants on the outside, we can just leave them alone. Looking at the integral on the inside, that's just dr over r. That's just a natural log. So we're going to get our constants, whatever they are. That's our 4 pi, or not pi, excuse me, 4 mu naught I L over 2 pi. And then dr over r is a natural log. So we're going to get the natural log of top minus bottom, 4L minus the natural log of L. And if we remember our log rules, when we subtract logs, we can divide them. When we divide 4L over L, we just get 4. So our final solution here can be 4 pi IL over, that's not a pi, jeez, I keep doing that, 4 mu naught over 2 pi natural log of 4. Okay, so that's what we can get there for that answer. If we wanted to reduce this, say 2 over 1, we could do that. I'm not going to bother. Okay. Starting at time equals 0, the current in the long wire is given as a function of time by I naught times e to the minus kt, where I naught and k are constants. The current induced in the loop is in which direction? So when I look at this here, this is an exponential decay, which means my current is decreasing over time. I have some graph and it's going down like that, where this is some I naught. Since my current is decreasing, when I run my right-hand rule here, I'm getting less flux going through the loop, so I need to increase it. If the flux is coming through the loop and it's increasing, when I right-hand rule, I'm going to get a counterclockwise direction of that. So I get a point for just the check mark. I could justify all that by saying a decreasing current means the magnetic field is going to have to, the magnetic field is decreasing, so more magnetic field needs to be gained in there through Lenz's law. That will give me 2 points. If I just want to get one quick point, I can say right-hand rule, and that will give me just one of 2 remaining points. Okay? But I could describe the whole Lenz's law there. Oh snap, someone is at my door. I gotta pause this.